Hello, this is Donghwan Shin from University of Luxembourg. I'm going to talk about a paper titled A Theoretical Framework for Understanding the Relationship Between Log Parsing and Anomaly Detection. This is a collaboration with Zanis, Ali Khan, Domenico Bianculli, and Lionel Bryan, all from University of Luxembourg. Software execution logs record the state and event of the system at runtime, which are very valuable information. Furthermore, logs are often the only record available for investigating the system's runtime behavior. And so log-based analysis, like log-based anomaly detection, has been widely used to automatically decide if the logs contain any anomalous patterns that do not conform to the nominal behavior of the system. You can see some of the example log messages below. By seeing the messages, we can easily identify that what happens during the execution of the system. One of the essential pre-processing steps that are common for any kind of automated log analysis is this log parsing, because automated log analysis requires structured logs, whereas the input logs are usually free-formed or semi-structured text strings printed by logging statements like printf or logging.info included in the source code. Let's look at this example. From this logging statement, by executing the system, we will have a log message. Looks like this. You can see that the variable block ID, which was in the source code, is now replaced as a concrete value that is determined at runtime. And you can also see that this log message is just a string, and there is no format for that. Without looking at the source code, we cannot identify which part is the variable and which part is the fixed. What the log parsing does is exactly that, tries to identify some key information and sometimes trying to identify event template, which is composed of fixed parts and variable parts. In this case, this fixed part characterizes the event of success verification, and the variable part, which is indicated by star, shows that the position of a runtime parameter, which will be replaced as a variable, as a value at runtime. The motivation of this work is that no existing work has thoroughly investigated the impact of the quality of log parsing result on anomaly detection. Indeed, the quality of log parsing result is not easy to define precisely because the concept of quality is somehow not clear. However, if we focus on anomaly detection only, then we can define the quality of log parsing in that specific respect. And that's what we are going to do. In particular, the concept of ideal log parsing result with respect to anomaly detection has not been defined and formalized yet. And that's what we will do throughout this slide. Specifically, this kind of issue makes it difficult, for example, to determine if the root causes of inaccuracy in anomaly detection are due to the limitations of log parsing techniques or not. One of the main contributions of this paper is the fact that we propose a theoretical framework for defining and discussing what are ideal log parsing results for anomaly detection. The behind idea is to consider log parsing as an information abstraction process that converts free-formed input logs into structured logs. Since automated anomaly detection relies heavily on the structured logs, its best operating conditions are when the minimum amount of information that is necessary to distinguish normal from abnormal behaviors is presented in such logs. We formally define the concept of distinguishability and minimality here, which further leads to the definition of ideal log parsing result. We also discuss practical implications and present some future research directions in the end. I first want to define the notion of logs, log messages, normal and abnormal logs. A log message M is a string printed by a log printing statement, logging statement in the source code. And a log is basically a sequence of log messages, which is denoted by this angle bracket of messages. For a set of logs for a system, we can consider a set of normal logs that represent a normal behavior of the system. The other logs of the system will be, of course, abnormal logs. And then the set of normal logs is represented by L subscript N, instead of abnormal logs are represented by a set of L subscript A. One important thing is that definition 2 is independent from the nature of anomalies, meaning that we did not specify any specific characteristics of the anomalies we are considering. We kept generic intentionally. And it only assumes that normal and abnormal behaviors are known and distinguishable in the logs. And that's the reason why when we calculate the intersection between Ln and La, there is an empty set. Based on that, we can develop the idea of log parsing as an abstraction. Basically, log parsing is a process that converts original logs composed of free-formed messages into structured logs by extracting key information from individual messages. For example, Drain, one of the most widely used log parsing technique, extracts event templates characterizing the events of the system under analysis as well as the variable paths. But this key information extracted from the log parsing technique can vary depending on techniques. And we can consider the log parsing as an abstraction process that generates abstract key information that represent multiple specific messages. For example, as you can see from the example below, the log message has a specific value for the block ID, but in event template, we have a generic variable, which can cover not only the specific log message we have in the screen, but also the other messages like verification succeeded for the other block IDs. In this sense, we can say that log parsing is basically a log information abstraction process. Based on the idea, we can define the log parsing as an abstraction function. Given a set of log messages M and a generic set of log parsing result A, a log parsing approach can be represented by an abstraction function tau, which takes M and goes to A. To keep our representation general, we introduce this abstraction function, and the definition of A, a set of generic abstraction result, is left generic to accommodate different types of log parsing results. Based on the definition 3, we can also extend the definition of log abstraction to the level of not from the log message to the log. So here, the abstraction of log is basically the sequence of abstracted log messages. And likewise, we can also extend the definition to the level of set of logs. And here, the abstraction of set of logs is defined by the highlighted part. I want to show you some learning example for that. Consider a set of logs composed of 3 logs, L1 to 3, and a log parsing approach where the messages A, B, C, D are converted to 1, 2, 3 as shown in this example. The log parsing approach can be represented by an abstraction function tau ex, such as tau ex A goes to 1, tau ex C goes to, and so on. Using this notation, we can also we can also represent the abstraction of logs. For example, the abstraction of L1 is the sequence of abstracted messages, which is the sequence of 1, 1, 2. Likewise, we can also present the abstraction of the other logs. Finally, the abstraction of set of logs can be represented by this, And in the end, we can see that the original logs can be abstracted as the set of sequences. Each of them is represented here, 112 and 113. Based on that, we can define one of the important concepts that is required for discussing the ideal log parsing result, which is distinguishability. As we saw, log parsing abstract given set of logs into the abstraction result, which is the input of main anomaly detection step. And if normal and abnormal behaviors, abnormal logs are indistinguishable in the abstracted result, then it is impossible to correctly identify abnormal behaviors from it from the perspective of main anomaly detection technique. Using that, we define the distinguishability concept, basically using the intersection between the abstracted normal logs and abstracted abnormal logs. Of course, the intersection must be empty. And in this case, we can say that after the abstraction, the distinguishability is still maintained. And in short, this is called de-maintaining. So let's go back to our running example and see how the de-maintaining concept works. Let's additionally assume that L1 and L2 are the normal logs and L3 is the abnormal logs. As you can see in the figure, these normal and abnormal logs are at the first place, of course, distinguishable. Definitely ABD is distinguished from the ABC and BAC. After the abstraction, we will have this abstraction of normal logs and abstraction of abnormal logs, which are 112 and 113 respectively. And then again, we can see that still the normal and abnormal logs are distinguishable even after this abstraction. And that we can say, okay, the log parsing result is de-maintaining, meaning that the distinguishability has been maintained after the abstraction. However, distinguishability is not enough. For example, consider an abstraction function, which is tau equal such that always returns the input message without abstracting anything. Naturally, this function leads to the de-maintaining log parsing result because by definition, a set of normal logs and set of abnormal logs without abstraction, there is no intersection. However, it is clear that it is not something that we want to have as an ideal log parsing result because there is no abstraction at all. So the observation we can have from the example is actually as long as log parsing results maintain the distinguishability, a higher degree of abstraction is better because it leads to better operating condition for anomaly detection. This is because it minimizes the information contained in the input, which is the structural logs for main anomaly detection engine, so that the main anomaly detection engine does not need to consider a large structural logs, which takes too much time and probably it will result in inaccurate result. Especially because these anomaly detection engines are mostly based on machine learning, and therefore more abstraction can significantly improve the learning performance by reducing the dimensionality in machine learning techniques. So we need to formalize the concept of information to minimize them. And to do this, we consider unique entities, which are the unique abstracted messages in the log parsing result. And this is the formal definition. And if we look at the running example again, as you recall, we have a set of sequences, 112 and 113. And by looking at those results, we can easily see that after the abstraction, we have 3 unique messages, 1, 2, and 3. And therefore, we have the information, which is the set of the unique abstracted messages, which are 1, 2, 3. Notice that this information gets smaller as the abstraction function abstracts the given input logs more. Based on this, we can define the minimality of log parsing result. Conceptually speaking, log parsing results must be de-maintaining and at the same time have the minimum information required for the demaintaining. And that's the definition. And let's just move on to the example. Again, recall that in our running example logs, we have demaintaining results, and the information contained in those results is the three messages 1 to 3. And it is represented by this figure. You can see that the after abstraction, we have distinguishable normal and abnormal logs. About what if we have another low parsing result, which is represented by tau nu, which further abstract these given example logs by merging the abstract message 1 and abstract message 2 into 1, 2. Then visually, we can see that this new abstraction function, new log parsing approach will lead to this 1, 2, 1, 2, 1, 2 for the abstraction of normal logs. But for the abnormal logs, after the abstraction, it will be 1, 2, 1, 2, and 3, which is still distinguishable from the normal logs. However, at the same time, we can see that the unique messages after the abstraction are now only 1, 2, and 3, which are smaller than the information which was in the previous example. In that sense, we can say that this new abstraction function, new log parsing approach, result in the ideal log parsing result, which is minimally demaintaining. One of the applications that we can use this theoretical framework is the localization of the causes of inaccurate anomaly detection result. When the anomaly detection accuracy is not 100%, this theoretical framework can help where the problem can help find out where the problem lies in the log parsing step and in the main anomaly detection step, or in both. Specifically, we can categorize the three cases. First, if the log parsing result is minimally demaintaining, meaning that it's ideal for anomaly detection, then the main anomaly detection step must be the problem. If the log parsing result is demaintaining but not minimally so, then making the log parsing result minimally demaintaining could significantly increase the anomaly detection accuracy, because as I said, anomaly detection is based on machine learning, and reducing the dimensionality will significantly increase the performance and accuracy of machine learning techniques and anomaly detection engine. And then the last case is the otherwise case, which means the log parsing result is not even demaintaining. And in this case, it is inevitable because of the low quality log parsing result. However, one can further investigate the specific issue, why it happens, especially focusing on the intersection between LA and LN after the abstraction. And by doing so, we can exactly understand what prevents the low parsing result from being demaintaining. In conclusion, we discussed a theoretical framework that formalizes the concepts of distinguishability and minimality, which are essential for defining the ideal low parsing result for anomaly detection. We also discussed a practical implication for researchers, and you can find out more implications in the paper. There are several future research directions. For example, since the ideal log parsing results are defined, but there is no existing way to efficiently and automatically generate those ideal log parsing results for a given system, maybe we need to implement and develop and implement an efficient algorithm for automatically generating ideal log parsing result for experiments. We can also tailor existing log parsing approaches, especially for anomaly detection, because generic log parsing approaches do not consider distinguishability and minimality, but they are very important for anomaly detection, as we discussed before. More empirical studies are also welcomed, and more runtime applications can be discussed. You can find out more details in the paper. Thank you for watching this video, and please feel free to contact me if you have any questions or ideas to discuss together. Thank you very much.